Hey everyone, uh, can you hear me? Hello.
Hello,
Hi Shraddha.
I can hear you.
Yeah.
Hi, Mukta.
Yeah. So I am the TA for this course, and
Okay, okay.
yeah. So I think we can wait for a few more minutes. Maybe some more people will join. Then I'll start.
Okay, okay,
Okay.
ma'am.
Yeah.
Okay,
I was just checking the mic. Thanks.
okay, okay.
Okay. Yeah. Hi. So can you see my screen?
Yes, now we can see.
Okay. Thanks. So I think I'll start now. People will join. Like they can join.
Okay, okay.
Yeah, so welcome to the course. So this is the first tutorial session for the course of Fundamentals of Micro and Nanofabrication. So for this first tutorial, we'll be mostly dealing with problems and some example problems from the week one of what Professor Sushoban has taught. So yeah, this course has two instructors, Professor Shankar and Professor Sushoban. Both of them are from Sense Department, Center for Nanoscience and Engineering at IISc. And I am Mukta, the teaching assistant for this course. So I am a PMRF student, and I'll be doing some problem solving sessions for the course. And yeah, I'm also a PhD student at Sense and I work with Professor Shankar. So you can reach out to me at this email address if you have any doubts, or you can just ask me in the tutorial sessions. Okay, so yeah, about me, I work at Photonics Research Lab. So we basically work on integrated photonic circuits, and this lab is headed by Professor Shankar, as I said. And yeah, so we target different applications in data communication, signal processing, sensors, even optical computation. Yeah. So yeah, without wasting much time, let's start with the first problem. So first, I thought of doing an example to like give a flavor of the general process flow of for making any nanoscale or microscale device. So let's say we want to make a voltage divider circuit. So in this figure, we see a simple resistor network. So there are two 1 kilo ohm resistors and a different resistor of 8 kilo ohms, and they are connected in such a way. So say I want to fabricate this circuit uh, in the nanofabrication facility that we have here at Sense. So what I will do first, I will first make a layout of it. So I'll first open some software like KLayout and make a GDS file of it. So so basically what I mean to say is, so this is just a circuit with circuit symbols, right? So we need to have a physical layout in mind when we want to make a device. So the physical layout for such a circuit would look somewhat like this. So here, uh, so the darker wires, these are basically the resistors. So we have two resistors of 1 kilo ohm. They are probably these two resistors, and then there is an 8 kilo ohm resistor, that is this longer one. So basically we just have a layer of resistive material that we have patterned to form these resistors, and then these bigger patches, they are they are probably made of a metal that is not very resistive, and these boxes are for the contacts. So um, uh, I just don't want a circuit, right? I want to pass, like I want to give some voltage or measure some voltage across different resistors. So for doing that, I need to probe this device, and to probe this device, I need these metal pads or like to make contact with the rest of the circuit. So yeah, so this is the layout that I want to fabricate in NNFC. So NNFC is the fabrication center at Sense. So how will I go about doing it? So this is not just for NNFC, like for any clean room fabrication, what is the process flow for fabricating such a device? So let us look at it. Um, yeah. So yeah, so I made it as a type of a multiple choice question. So the first option is we clean a silicon wafer. So we take a silicon wafer. So that is the like basic step. For any micro and nanofabrication, most of the time we do it on a silicon substrate. It is widely available now, and technology is quite mature. Like technology in the sense that like we can easily deposit various different kinds of materials on silicon. We know how to we know a lot of recipes for metal deposition, etching and everything on silicon wafers, and they are readily available also. So the first starting step of any nanofabrication like process flow will usually be take a silicon wafer and clean it. So I think Professor Shishobhan has also talked about uh, wafer cleaning in his first few lectures. So so this clean silicon wafer, this step might have something like take a new wafer and then do RCA 1 and 2 on it. Then probably an HF dip to remove the native oxide that might have grown due to this RCA. So not yeah. So we know that RCA can do, so RCA 1 can do organic cleaning, organic contamination cleaning. RCA 2 can do metal contamination cleaning. But then these are oxidizing steps, so the top layer silicon can like there might be some oxide that might form on the top layer of the silicon, so we use an HF dip. So yeah, so that is that will come in the later part, but for now, if I do this kind of a process flow, so first I clean a silicon wafer, then I do a metal deposition, and then I do a pattern transfer. Will I be able to? Hello? Uh, did some. I heard something. Okay. Yeah. So the first step is cleaning the wafer, second metal deposition, and third pattern transfer. So basically what I'm saying is, if this is the cross-sectional view, this is my silicon. I am putting, say, some metal by some sputtering or some like CVD step. Say I put gold, and then I do a pattern transfer. So by pattern transfer, I mean I like lithography and etching step. So let us assume that I already have a mask. So I have gotten a mask from the mask manufacturer of this, uh, like for this design, and now I just transfer the pattern of that mask onto my onto the gold layer here. So I'll just cover some parts of this with a photoresist, and the rest will get etched. So basically the end product would look somewhat like silicon and metal on top of it. So will this work? Does anyone want to answer? Hello? Um,
Hello.
Hello, like, am I making sense here? Or is this too many new jargon?
Mukta,
Huh,
can you check the messages? So I have the basic question,
huh.
where which wafer to use. I have put it in the messages.
Okay, I see. I was not actually checking the messages.
No problem, no problem. Thank you, because this
Uh,
is all new to us.
I see. Yeah, yeah, yeah. Which silicon wafer to use? Yeah, I get it. So you are asking if I need like N dope silicon, P dope silicon, all those things, right? Or
Right,
we
right, right,
need single side polish, double side polish.
right, right, right.
Right. So this is a very simple circuit. In this, basically, whatever you use, it will work. Uh, as long as the process flow is right, is good enough. So, right. So, yeah. So there are things like you have single side polish and double side polish wafers. So single side polish will be sufficient for this because we don't really want to fabricate anything on the other side of the wafer. We are not doing any process on the back side. So single side polish will work. Um, Sometimes you have to worry about the backside roughness, like if you're using some sophisticated lithography tool in which um, in which it might happen that the vacuum might not form correctly if the backside is too rough. So in that case you like, even though you use a single side polish itself, you check the backside roughness, otherwise that is fine. Then n doped, p doped, we are actually saying that these are actually metal layers, so this is not silicon. So here we don't care about the doping of the silicon as much, so the current should not be passing through the silicon. So if the silicon is more resistive, it is better, like that. So we don't care about if it is n doped or p doped, because anyways I'm saying that we are depositing metal on top of it. So um, yeah, that part is there. What other specifications you might wonder? Size and all. This is a very small device, like, doesn't matter. Yeah, prime grade or test grade. So that you have to consider. So your final device should always be on the prime grade wafer. So so there are different grades of the wafer. So based on the purity. Very pure wafers are the prime grade wafers, and they are usually used for electronic devices. But when you want to optimize certain processes in the device fabrication, you can use something called test grade wafers. So in test grade, these are not as pure as prime grade wafers, but say I want to deposit a metal layer and optimize the etching of the material of the metal on top. Then I don't necessarily. So for this optimization step, I will require a lot of wafers, right? So if I use prime grade wafers, that will be very costly for me to optimize this. So in those cases, we use the cheaper test grade wafers, but the final device we always make on prime grade wafer. Yeah, so that is about the substrate selection. So yeah, so this first process, it will not work simply because I am not putting any insulation between the silicon and the metal. So we know that silicon is a semiconductor, right? So if silicon is a semiconductor and this is a resistive material that I am putting here, then like the current will also leak through the silicon material. Right. So through the substrate, that is the silicon, because it's not an insulator, it's a semiconductor. So what we would ideally want to do is put an insulator in between the silicon wafer. So silicon will just act as a base. On top of the base, we'll have an insulator. So this insulator can be just SiO2. So we can thermally grow oxide on top of silicon. How we do that we will learn in the subsequent weeks. But for now what we need to understand is there exists a process by which we can deposit oxide or grow oxide on top of a silicon wafer. So the silicon dioxide is an insulator. So it's a very good insulator. So once we deposit this and then put metal on top of it and then pattern transfer, we won't see any current leaking into the substrate. I hope I made myself clear. Uh, so that's why we put insulator. So, but that is not all. So when we looked at this design, we had actually two layers. So this the thicker pad layer. This has to be have very less resistance because we want all the resistance drop only across the resistors. So this is the resistive layer, and this is the not so resistive layer. And also the thickness we have kept it large so that the resistance is minimum here. So yeah, so we need two layers. The single metal layer is not what we require, so we need to do two metal deposition steps. So this process flow is also not correct. So the next one, let us look at this. So we have a clean starting wafer. We deposit silicon dioxide or any other insulator on top of it. Then we put a resistive material. So this is for making these resistors, this small 2 and this one big one, 8 kilo ohm resistor. So these we are making using this resistive material. Now we have deposited the resistive material. We need to transfer this pattern of, so we want to make it into these wires. So it will be evenly deposited all throughout the wafer. We will etch out the remaining and only keep these wires. So that step is called pattern transfer. So once resistor material is deposited, we do the pattern transfer. Then again deposit metal. So this is low resistance metal. Sorry, that is this pad material. And then we do another pattern transfer. So now will this work? Just take a wild guess. I am actually not able to see the chat box, so it is better if you just speak up. I am not used to Google Meets also. Uh,
Ma'am, can you please explain the pattern transfer again? Like after depositing the resistor material, so there are like three resistors, so 1K, 1K, and 8K. So after this,
you mean to say how do I put this pattern on
mhm.
top of the wafer, right?
Yes, yes.
Yeah. Okay. So yeah. So the pattern transfer process. So first, why did I design these resistors like this? First, we know that the resistance of a material will depend on the length, the width, and the thickness. Now, when I'm depositing the resistive material, sorry, I think I didn't take the pen. Huh. When I'm depositing the resistive material, so this says my resistive material on top of my oxide, so there is SiO2 and there is silicon down. So when I'm depositing this material, the thickness of the material is same throughout, right? So we cannot vary the thickness of this resistors. So what we can vary is the length and the width. So to
Mm-hmm.
make an 8 kilo ohm resistor, we just made a longer resistor.
Okay,
So
okay.
that part is clear, right? The
Huh.
design part. Why we
Yeah, yeah,
designed one as long and other two as short.
yeah, yeah, yeah.
Yeah. So once
Yeah,
we have designed
Steve,
this, huh,
I have one question.
huh.
Apart from changing the length, can we use the doping, the type of doping and the amount of doping by changing that itself? We can change the resistance. Am I right?
So the thing is, uh, when you dope this material, it will get doped throughout the wafer. So how will you dope only this part and not the other part? So what we are actually doing is we are coating the, like we are depositing the material throughout and then
Okay.
etching the parts, right? So the
Okay.
doping
Okay.
will be the same for all the three wires.
Okay. Okay.
Or
Okay.
you have to design a specialized process in which you that will become more complicated.
Okay. Okay.
Yeah.
Okay. Okay. Right.
Yeah. So next what we do is we take a photo mask. um, so now we want to just keep these black lines and remove the rest of the resistive material. So to do that we do something called as photolithography.
Okay.
uh, Professor Shushoban has, I think, talked a little bit about this. So what
Yeah, yeah.
is so what we do is we just coat a photoresist. Can I take another color maybe? This is not seen. So we will coat photoresist by some process of spin coating. So this is basically a polymer. So we'll coat it on top of this, and then we'll have a photo mask. So this mask will already have the design that we want to write. So some places it will be open. So this is just a cross section view. Some places it will be open and some places it will be uh, closed. So like basically we'll have light, will shine light on top of this mask, and the shadow will be reflected on top of this photoresist. So because of this, the pattern will be transferred from the mask to the photoresist. So till this part, is it clear? So the photoresist will, so so in some regions the photoresist will solidify, and the rest of the regions, when we put this into something called a developer, the rest of the photoresist will go. So
Ma'am, I have a doubt here, like
huh,
this part only, that by saying that pattern is present on the mask, like already present on the mask, so
hmm.
that pattern itself is this the outside thing, that pad portion you are saying, that for contacts and all that,
No, no,
because
no.
resistors we are,
So
or the whole layout design is the.
yeah, we'll actually make a mask which will have the entire layout design.
Okay, okay. Mm-hmm. Okay.
So this has say one layer for the resistor, one layer for the metal. So the mask itself will have multiple reticles. So in one reticle we'll just have the resistor wala portions. In other
Mm-hmm.
reticle we'll have the contacts. So one
Okay,
layer
okay.
will have one thing.
Okay, okay, okay.
So these
Understood.
masks we get it made by mask manufacturing companies are there. They
Mm-hmm.
will make them. If you don't have a mask ready, you can go for something called as direct writing. So direct writer is a tool that will have a laser, so a light source that will move on top of each and every box that you want to write, and then like it's like a pen and it will write it on top of the wafer, mm, like how we write with a pen on top of a notebook, like that. So that is
Mm-hmm.
direct writing. But I thought talk about photolithography because sir had talked about this in class. That's it. And
Mm-hmm.
this
Yeah.
is also more like when we want to do wafer scale, this is more feasible like that.
Okay.
So you get this mask made, and then you transfer the pattern onto the photoresist. So photoresist is a light sensitive material. So wherever the light will shine, the bonds there will be weaker compared to the where the light did not shine. So these bonds will easily dissolve in the developer solution, and once so with the developer we can remove those parts of the photoresist. So now we only have photoresist at certain positions. Now when we etch this device, this photoresist will actually protect our this resistive material that we put. So the material will get etched only in these locations. So these parts will disappear. Is it okay?
Yeah, yeah, understood. Yeah, yeah.
Huh. So
Thank
now
you.
we have the resistor here. Right.
Yeah, yeah.
Okay. Thanks. Huh.
Hello,
So now we just need to remove this photoresist. Hello?
Mukta, can you come again? I actually missed this figure B. I'm not able to understand how to differentiate between 1 kilo ohm and 8 kilo ohm.
Right.
Can you just repeat it? Because A figure I can correlate, these are in series, but how to, how to differentiate among in figure B?
Okay. So basically, what I was saying is a 1 kilo ohm resistor. Uh, so the resistance of a material depends on. Uh, so first of all is resistivity. But since we are keeping the resistor material constant throughout the wafer, the resistivity will be constant. So what we can change? We can change the length and the width, right? So the length of the uh, so so basically the 1 kilo ohm resistor will keep the shorter length and 8 kilo ohm resistor will keep a longer length. That's it.
Okay,
So
okay, okay. So,
resistance is directly proportional to L by
right, right.
width
So
into
that
thickness.
the longer side of the wire which is curved is the 8 kilo ohm,
8
right?
kilo ohm resistor.
Oh, thank you, thank you.
Okay, yeah. Right. So now we understood what is pattern transfer, right? Okay, I hope it was clear. Huh. So this third thing, why? So I'm telling you that this is wrong. Can someone guess why this might be wrong? So we cleaned the starting wafer. We deposited insulator to insulate it from the silicon. Then we put the resistor material. So we wrote these lines 1, 2, and 3 by doing a pattern transfer. Then we put the metal for the pads, the bigger pads, and the contacts. For those we put the metal, and then we did a pattern transfer. What might be wrong in this? Just take a guess. Um, okay, so thing is, if we are putting the resistive material and directly uh,
The metal can deposit on silicon.
exactly, not on silicon, it will deposit on oxide only. But it is always a better thing because what will happen is, so I have this silicon, then oxide, so it will not deposit on silicon anyways. So every part of silicon is covered with oxide. Then I have this resistor material somewhere at some places, right? So if I just directly put the metal on this, it will also uh, overlap with the resistor wires. So that will create a short. So the general practice in such situations is to put another insulator layer. So it might happen that you have some resistors here, here, here. Now contacts want to go somewhere from here to here. Then it might overlap with the resistor at this place, and that will create a short. So the general practice is to put the contacts like in a different layer. They're already in a different layer, but put an insulator in between. So that part we skipped here. So there should be an insulator deposition, and not just an insulator deposition, we also need to pattern this insulator. So at the positions where we want the contact, this insulation uh, so at some positions we do want the contact, right? So if this is my metal and I put an insulator layer on top of it, then so this is the resistive metal, and then I am putting the non-resistive metal. So directly by putting it doesn't work. We have to first pattern this insulated layer to open these regions, so that this metal forms a contact with the resistive material. So um that's why the correct process flow is this. So first we clean starting wafer, then we deposit an insulator, then the resistor material will be deposited. So we have patterned this. So there is a silicon, then on top of that there is SiO2, then there is the resistor material, then there is an insulating layer, and this insulating layer we make some holes, so that the top metal layer makes contact with the resistors, and then we pattern the metal layer as well to make the pads. So this is the correct flow. My diagrams were not that good, but uh, I hope you got the idea. Okay, so let's move on to a bit easier question. So which of these statements are correct? So the first statement is microelectronics has attained higher performance despite falling costs. The second is smallest devices that we can make are of the width of a human hair. So human hair is somewhere around say 100 micrometers. So third is it is impossible to deposit films that are 1 atom thick, and fourth is it is not possible to tune the conductivity of semiconductors. So
First one,
yeah, right. So you're saying the first one is the correct option, right? So yeah, you're right. So I can hear myself actually. So what I mean is, uh, yeah, microelectronics has actually attained higher performance despite falling costs, and this is because we can use microfabrication, nanofabrication, to make devices at very small scales. So of the order of 25 nanometer critical dimensions, and that has actually helped us in reducing costs. So these days we all possess electronic devices which have IC chips, and it's not that expensive also. So earlier it used to be much more expensive to possess a computer or electronic device, but as time has progressed, the technology has progressed, we are getting higher performance and the costs are also reducing. So yeah, that's true. So why is the second one not true? Because yeah, as I said, we can make devices in the nanometer scale. And hello, yeah. So it is impossible to deposit films that are just 1 atom thick. That's also not true. We have epitaxially grown films. So epitaxy is when we basically do single atom film depositions. So this is done, and uh, this is done in a lot of cases. Like most silicon like used in CMOS are epitaxially grown. So this is not impossible anymore. And I think professor has also shown an image of a epitaxially grown silicon on, I don't know on what, but yeah, he has shown an image, I think. So yeah, it is not possible to tune the conductivity of semiconductor. This is obviously not true. We all know about doping, right? So silicon is a semiconductor, and intrinsic silicon, say, has a band gap of something like this. So this is the conduction band. This is the valence band. So by doping silicon, we can create the dopant. So we'll have dopant energy levels somewhere close to the conduction band if it's an N type, or close to valence band if it's P type. And this doping, this doping, we'll have charge carriers that will have that will generate extrinsic charge carriers in the conduction band. So that will actually tune the conductivity of the semiconductors. So okay, yeah, yeah. What is the purest silicon you can buy?
Hello.
Hello.
Good evening, ma'am. Can I ask something before we move on to the next question?
Sure.
Yes, ma'am.
Huh.
Ma'am, I wanted to know two things out of curiosity. Just apart from attending the watching the learning from the lectures from both the learned officer professors and taking the assignments, is this me like lectures that you are providing? Is it compulsory for getting the certificate, or how we will be learning from it? Can you please tell, because it's going on very smoothly. Was out of curiosity, I'm just asking.
Okay. Yeah. So this is obviously not compulsory. What the general
Okay.
idea is that I'll be doing some problems that will help you in doing the quiz questions or the assignments, and I think you'll be taking the final exam also, right? So
Yeah.
yeah, so I'll be discussing, like, some of these problems are the assignment problems that I had done during my course. So this might be helpful for you
Okay.
for like appearing for the exam and things like that.
Okay. Thank you, ma'am. Thank you.
That's
Thank
it.
you for the
It's not
info.
compulsory,
Yeah.
and yeah, it's totally
Okay.
up to you.
Okay. Thank you.
Okay. Huh. So which is the purest silicon you can buy?
The fourth one,
Yeah, you are right. In some cases we can even go even more purer silicon. Yeah. So this is being possible due to the zone refining techniques. So that sir might have taught. So CZ method, FZ.
Uttam, I have a question.
Yeah.
See, in the tutorial, in
Hmm.
the recent quiz, the question regarding the first question is like which technique is to make the wafer. Whereas both the technique which professor has discussed, they are to make the ingot, not the wafer. Uh, so
Like which question?
this,
This one,
so
right?
not this one. So in the assignment, in the first assignment,
Oh, you're talking about the assignment that has been shared.
yes, 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 yes.
Okay. What was the first question? Can you tell me?
Yeah, yeah, I can tell you. So how are silicon wafers produced from ingot,
Huh.
right?
Huh.
So the options were CZ method and FZ method,
Hmm.
and then both and none of the above.
Hmm.
So first appearance, it appears like CZ and FZ are both the methods which can make the wafers.
Okay.
Whereas, but the thing is, using these methods, we are only making the ingots. So I got actually confused. Can you help me? Because how we make silicon wafer, it's from the ingots, and these are the two methods. Why I asked this question now is because you are asking about the purity, right?
I
In this
understand.
question.
Okay, so sir has taught about these two methods. So instead of looking at the question like how we make them from like how we use this method wait, what was the question again? How are we making wafers using which method, right? FZ
Yes,
method or
yes, yes.
CZ method. So think of these as ways to purify the wafer, purify the ingot. Say,
Right,
like
right,
instead of having silicon in the melt form, I gave you a polycrystalline silicon ingot. Ingot is just a shape, right? At the end of the day. So I give you a polycrystalline silicon ingot. You can melt it, you can solidify it, you can partially melt it, do whatever, and get wafers out of it. So which processes are used? That is the question.
Um, okay, but
At least that is
my
what I
question.
think it is.
Okay, because yeah, even I got confused. It appears one of the user has written both, but to my opinion, actually, we both the methods are just to produce the ingot. After we have the ingot, we use the
Ingot is not
diamond
like,
saw.
okay. So if you remember the FZ method, we already start with an ingot, right? Ingot is just the shape. It's not like we are
Right, you're
producing the
right.
ingot. We the end
Right.
product is always the wafer.
Okay.
At least I think so. I don't know the correct answers to the assignment, so don't trust my answers. Also, they asked me to not like discuss the current assignments, so I don't know.
Yeah, yeah. Okay.
Yeah,
No problem.
right. Yeah, about so this is about the binary phase diagram that professor has talked about. So the figure shows the binary phase diagram of germanium silicon alloy. So, so binary phase diagram is basically when we have two materials in a mixture, and this mixture can be in the solid state, liquid state, or it can be partially solid, partially liquid. So that is this center part. So anything above, so this is the temperature, and this is the atomic percent silicon. So this point corresponds to 100% silicon. This point corresponds to 100% germanium. So yeah, so anything above this line will be liquid mixture. Anything below this line will be solid mixture. So in middle we have both liquid and solid. So idea is silicon has a higher melting temperature than germanium. So obviously their mixture will uh, like uh, have some melting temperature in between the two. So yeah, so that's how what is the basic idea of a binary phase diagram. So say the question is I heat the solid alloy of 50 atomic silicon. So it's a solid, so it will be somewhere in this region of 50 atomic silicon. So 50% atomic silicon to 1150 degrees Celsius. So somewhere till here. So I had a solid germanium silicon alloy and I heated it till this point. What is the percentage of silicon in the solid form? So what is the percentage of silicon in the solid form? So to do this, we need to understand how to read a binary phase diagram. So um, at 1150 degrees Celsius, at 1150 degrees Celsius, if we had a mixture in which uh, the atomic percent silicon was somewhere around this value, then the entire mixture would have become a melt or liquid, right? So but we don't have atomic percent silicon below this 23 or 22 value. Okay, we have it above that. So that is why the entire mixture has not become melt, but some part of it has become melt and some part of it has become solid. So so the way to read this binary phase diagram is if we draw a line from the 1150 degrees Celsius temperature, then wherever it intersects this liquidus line, so this line is called liquidus, wherever it intersects this line, that is the that point gives us the atomic percent silicon in the melt or liquid. So in this case, the atomic percent silicon in the liquid phase is somewhere around 23%. Similarly, in the solid phase, we get it by using this line. So in the solid phase, the atomic percent silicon will be somewhere around, I am this, like this graph is not to scale, but 60%. Yeah, so these are the correct answers. Uh, so anyone has any questions? If not, we'll go ahead. So,
Ma'am, ma'am, can we go back
yes.
previous question?
Ah,
Ma'am, then you are saying the remaining percentage will be in between the solid and liquid, means 100
no, no, no,
minus
no.
58 plus 20.
Uh, so, what I'm saying is, see, if I would have heated it, so if the temperature was below 1100, then the entire thing would have been a solid. If the temperature was above some 1250, entire thing would have been a liquid. But since it is in the intermediate stage, some part is solid, some part is liquid. So in the mixture, we have some solid portion and some liquid portion. So
So,
so in the solid portion, what percentage is silicon? That is the question.
okay, I got your question, but I'm just generally asking the percentage. What is the percentage between the solid and liquid? How many percentage silicon is liquid and solid? Both.
Yeah, so that was my next question.
Okay, sorry.
Yeah, no problem. Huh. So, so I put it as a continuation question. So, what is the percentage of alloy in the molten form? So, what is the percentage of alloy in the liquid form? So, it's actually quite easy to do this. So, I'll just say that let x be the fraction that is molten. So, I'll say fraction of alloy that is molten. Then naturally, what is 1 minus x? 1 minus x is fraction of alloy that is solid. Okay, so and from the previous question, what did we see? We saw that a percentage of silicon in melt is 22%. So in liquid is 22% and percentage silicon in solid is I think 58%. Right. So we know that the total silicon that we started with a 50% silicon. So the fraction of silicon should never exceed zero point 0.5. So what does that mean? That so percentage of silicon in liquid is 22% means 0.22 times uh, so the alloy that is there in liquid. So that is x. So 0.22 times x and 0.58 times 1 minus x. These both should add up to 0.5. Is this correct? So I'll write it properly. So the equation that we get from this is 0.5, that is the total silicon fraction should be equal to uh, the fraction in the molten state plus the fraction in the solid state. So by solving this we can get the answer. You can do this on your own and I'll just tell the answer x is equal to 0.22. So this is the correct answer. So this is the fraction of alloy that is in molten state. So naturally the fraction of alloy that is in solid state will be 1 minus 0.22. Is that okay?
Yes.
Yeah, okay. Thanks. Yeah, so the next problem. Which of the following impurities in silicon cannot be reduced by zone refining? So, so zone refining was taught in the class. So, so zone refining is basically just melting the silicon and then solidifying it, and based on the impurity. So just like we saw in the case of germanium, when we go towards the so the liquid, so when we heat it, the liquid will have lower atomic percent silicon, whereas the solid will have a higher atomic percent silicon. So basically, germanium likes to stay in the liquid form, and so that the silicon that we get in the solid form is purer. So most impurities in silicon actually show this behavior. So that is how we can just separate them by solidifying the silicon out of the mixture. So that is the general idea of zone refining. So yeah, so then I have given you some impurities and their distribution coefficient in silicon. So based on these distribution coefficients, what do you think?
Arsenic.
Huh? Hello?
Arsenic cannot be refined by zone refining, right?
Why is that? Like just based on the distribution coefficient, I'm asking.
I don't know it depends on distribution coefficient, but it depends on the gas it evaporates while producing that ingot. So we need that boron.
You are talking about gallium arsenide fabrication?
Yes.
No, no, no. So this I'm talking just about silicon. So uh, I have a silicon ingot with these impurities. Which of these will I not be able to remove by zone refining? I'm not talking about gallium arsenide. So first let us look at what is the distribution coefficient. Uh, Maybe you might remember the letter K that Prof had used. So this K is nothing but CS over Cl. So basically this is just the concentration of impurities in solid. I'll write it down. Concentration of impurity in solid upon concentration of impurity in liquid. Right. So if my K is less than 1, that means that my impurity likes to stay in the liquid state more than it likes to stay in the solid state. So there is less concentration in the solid state compared to the liquid state. If K is equal to 1, then the impurity will be, even when I melt the ingot, the impurity will have the same concentration in the melt as well as the solid. But when K is greater than 1, what will happen is the impurity will prefer to stay in the solid, and the concentration of the impurity in liquid will be less. So if you just look at this germanium example here, what do you think is K for germanium? Is it less than 1 or greater than 1 or equal to 1? So when we melted this germanium from solid to liquid, solid to this intermediate temperature, we found that the liquid portion had more germanium, so had less silicon, that means more germanium compared to the solid portion, right? So that means K for germanium is less than
Less.
1. Yeah, you're right. So similarly, now can you answer this question?
Oxygen.
Yeah, you're right. So it's very very difficult to remove oxygen using the zone refining technique. Um, Yeah, because it's more you do zone refining, the more oxygen will get concentrated in your ingot. Instead of uh, getting removed into the liquid, it will get concentrated in the solid. So we cannot remove oxygen by zone refining techniques. But it's good in a sense that it actually makes the wafer more um, strong, like mechanically. Yeah, like yeah, so that is the thing. So that's why when you look at the impurities in silicon wafers, most of the impurities will be very low, in like very low, parts per trillion low, but oxygen will be still comparatively higher. Okay, so that was about the distribution coefficient. So the next question is, if the device engineers need, so this is just a numerical, like uh, it's very easy. If the device engineers need metal impurities less than 10 per 11 centimeter cube per centimeter cube, what is the maximum metal impurity concentration in parts per trillion that you can allow in the silicon wafer that you are purchasing? So when you want to purchase a silicon wafer and your um, design requires that the metal impurities be less than this number. So basically it's just converting this number to parts per trillion. How will you do it given that the silicon atom density is so much? So this is if I need metal impurities less than 10 per 11 per centimeter cube, that means I have to have 10 per 11 particles amongst 5 into 10 power 22 particles per centimeter cube. So that means how many will we get? 10, 5, 10 per 12, so that I can just cut this 2. So this is equal to 2, 10 per 12 is trillion, right? I hope so. So this is becomes 2 ppt. So yeah, this is okay, right? So you might get such questions in your quiz also. So next is FZ method can form purer grade of silicon than CZ method. Why is this the case? Anyone wants to take a guess? Hello?
Multiple passes are possible.
Yes, second
Yeah.
option.
Okay. Yeah, that's the correct answer. Um, yeah. So in FZ method, what we can do is, so fluid zone method, uh, we can keep on purifying the metal by melting it again and again. That is not possible in CZ method. So, and why does that work? Can you just elaborate? Like, why does melting and recrystallizing again and again help us get purer silicon ingot?
Because of distribution coefficient, we can every
Yeah, yeah, yeah.
time we can push the impurity to the melt.
Hmm?
We can every time we can push the impurity to the melt because
Right,
of the
you're right.
distribution coefficient.
Okay, yeah. So that is the thing. I think that is clear now. Thanks. Yeah. So the next problem. For the silicon ingots made using Czochralski, that is CZ process, which of the following statements are true? The diameter of the ingot decreases if the pulling rate increases. The dopant concentration is constant for almost constant throughout the ingot for the segregation coefficient of K equal to 1. So this is again the same distribution coefficient. The dopant concentration is constant or almost constant throughout the ingot for the segregation coefficient of K less than 1. Prime grade wafers are more likely to be obtained from the starting part than the ending part. So there are multiple options that are true. So can you tell which all are true?
Option 4.
Option 4 is true. So prime grade wafers are more likely to be obtained from starting part of the ingot than the ending part. Yeah, and that we know is because, uh, do you want to answer that? Like, why is option 4 correct? Okay, then
Because
that,
we start melting the ingot, the
hmm.
silicon from the concentration, the amount of silicon in the melt will decrease.
Right, yeah, yeah, you're right. So the concentration present in the melt itself will decrease. Yeah, okay. So then when we try to recrystallize it, the number of impurities will be more in the, yeah, you're right. So prime grade wafers are more likely to be obtained from the starting part. So yeah, but there are more than one correct options. So what is the next true statement?
Option 1.
The diameter of the ingot decreases if the pulling rate increases. Yeah, that is in fact true. Um, the reason is a bit complicated. Like it has to do with the so the when so this is the melt, say, and we are pulling an ingot. So at this stage there will be some crystallization that is happening, so that has a heat that needs to be dissipated. So the heat dissipation can only occur across the area, like the surface area, but the heat is produced in the volume. So if the volume becomes too large, so the if the ingot thickness is, so the radius of the ingot is very um, big, then what happens is and we pull it fast, then what will happen is there won't be enough time for the energy to dissipate. So that is why we won't be able to make it the radius big in the first place. So there is some such thermodynamic kind of reason because of which the diameter of the ingot, it depends on the pulling rate. So the slower the pulling rate, the thicker ingots you can make. So obviously it also depends on the other things like the heaters that you have in the, like how well you are maintaining the melt temperature, how well you are stirring it, what is the rotation speed. It also depends on that. But if you just look at the pulling rate, the diameter of the ingot decreases if the pulling rate increases. So that is true. You're right. So among these two, which one is correct? Dopant concentration is constant or almost constant throughout the ingot for the segregation.
Option 3.
3. So dopant concentration is constant throughout the ingot for the segregation coefficient K less than 1. Why are you saying that?
I don't know the exact thing, but I knew that graph that surge through at that exponentially. That after a certain point, it becomes straight line. So I don't know perfect thing.
I I don't know what, like, I don't remember what he drew, but I think second one would be correct, right? Because uh,
Second one would be correct because k
yeah,
is equal to 1, no?
if K is 1, then so if this is my ingot and this part is molten, like, or say even in this case, if I'm like some portion is molten and some I'm making it a solid, since K is 1, then both melt and solid will have same amount of impurity. So regardless of how much I have pulled it outside, it will still be the same. So that's why I think that throughout the ingot, the dopant concentration will remain the same. Impurity, nahi, dopant concentration. Uh, I also think it is second one. I don't know which graph you're talking about, but I think it should be second one. Because when K is 1, what does it essentially mean? K is 1 means concentration of impurity in solid is the same as concentration of impurity in liquid. So at every stage, so in this case it's not impurity, it's dopant, but at every stage the dopant in the solid and in the liquid are remaining the same. So throughout the ingot they will remain the same even after the CZ process is complete. Is that okay?
Yes.
Uh, Do you want to explain why you think it's the third one? Because I did not understand. Or okay, I'll see the lecture and come back to you if he is like some graph or something. Okay. So the next problem, distribution coefficient is a fundamental property of silicon impurity or silicon and impurity both, or the growth method.
Option 3, silicon and impurity
Yeah,
solution.
you're right. Yeah, yeah. So it depends on the binary phase diagram, and it is unique for the combination of the two materials. Yeah, yeah, correct. Huh. So problem 10, silicon, germanium and tin are all group 4 elements. So what it's saying is tin is a metal, silicon and germanium are semiconductors, carbon is a, yeah. So carbon is a what, non-metal, insulator. So tin is a n-type dopant in silicon. So is it true or false? So what they're saying is, so tin here is a metal. So can it act as a n-type dopant for silicon? So n-type dopant means it's an electron donor type, huh? I could not hear you. Do you think it is true or false?
It's false.
False.
For n type of dopant, we use pentavalent and gravity.
Yeah. So yeah, so most of you are saying false. So yeah, that's actually the correct answer. You can't just because it's a metal, it won't act as an n-type dopant. So can you tell me which of these materials will act as an n-type dopant?
Like a phosphorus.
Right. So phosphorus will act as a n-type dopant. Yeah. So for others, I'll just tell. So silicon is a so it forms four bonds. It has four valence electrons, and so so it forms four bonds with the neighboring silicon atoms. So once we have to make it n-type dopant, if I put a, say instead of silicon I put a phosphorus, then it will have five valence electrons. So this extra electron will be free. Uh, so this extra electron will actually lie when I draw the Fermi energy band diagram. So this is conduction band, this is valence band. So this extra electron will lie somewhere over here. So you can call it as a donor level. And then this electron needs very less energy to jump towards the conduction band compared to the valence band electron. So that makes the conductivity of this material higher. So this is n-type doping. Similarly, in p-type doping, we can have a boron or some other this family. What is this called? Three family material. So what boron will do is basically if I have a boron here, then boron only has uh, boron only has how many? Three electrons. So it can form three bonds. So in order to form this bond, it can take an electron from a neighboring silicon and form this bond. So then the neighboring silicon gets a hole. So then we are forming essentially forming holes, and these holes are formed at the acceptor energy level here. So yeah, so then the electron can jump into this acceptor energy levels, and then we essentially get a get the electrons in the conduction band more easily. I think yeah, that was the explanation. Okay, so Yeah, that's about doping. So next, plasma can be used for both etching and deposition. True or false? So plasma is basically ionized form of gas for the purpose of fabrication. That is plasma. And so can
True.
it be used for both? Yeah, true.
True. Yes.
Can you tell me the processes in which plasma is used for etching?
Um, Argon ion etching, where we remove the metal or contaminants, or gold deposition, where we use plasma to deposit gold.
Yeah, you're right. Yeah, so the deposition step is sometimes also called sputtering, right? So basically, like you said, in deposition we just have a positive electrode, negative electrode, and we'll put the, so we'll have some gas. So like you said, we can have argon gas, and argon gas will ionize because of this electric field that we are putting. And then we'll have Ar plus and electron. So electron will move towards the positive, Ar plus will move towards the negative. And now if I have a metal here, this Ar plus ions will bombard the metal, and the metal the metal atoms will uh, will move towards the substrate, and that's how we can deposit the material on the substrate. So I am putting the substrate at the positive electrode, the metal that has to be sputtered at the negative electrode, and so that is the general idea of sputtering uh, that we know. So here we use plasma. Similarly, for reactive ion etching, so yeah, for RI we can use. So this is a dry etching technique in which um, again we can have such electrode like things. Uh, basically, basically give some voltage. Okay, and then this voltage will produce some plasma of a reactive gas. So this gas need not be argon, it will be usually some fluorine chemistry, chlorine chemistry, some chemistry, like some recipe that will be optimized for the substrate that you want to etch. So these ions will bombard on the substrate and etch away the substrate. And at some positions, like we can save it, as I said earlier, by using photoresist. So only wherever the photoresist is not present, those portions will get etched. So in such processes also we use plasma. Right. Yeah, so this is about the contamination policy. You have to tell me which of these processes are allowed. So let's go one by one. So, can you do a level 3 piranha clean of samples processed outside the clean room? So say you had some samples, um, you had to do some characterization of the sample and you took it outside the clean room. Now you want to bring it back inside the clean room and do some other processes, say some other deposition or, or any other kind of process. Can you do it by doing some form of piranha clean and then some other level 3 clean? Can you do it?
No.
No.
No. Okay. Yeah, so all of you have listened to the videos. That's nice. Uh, RCA clean wafer being brought back to level 1 wet bench for wet etch after metal deposition. So you had a new RCA clean wafer that was level 1 because it was a new wafer and you did an RCA clean on it. So after that you did some metal depositions along your process flow. Now can you bring it back to level 1 wet bench for wet etch?
No. No.
Yeah, why is it?
Metal deposition.
Right, so metal is the thing here. We can't bring metal in level 1 or level 2. So can you do this? Level 1 clean of sample post level 2 clean. So say I have a level 2 sample. I want to bring it back to level 1 for some other process which requires very clean samples, level 1 samples.
Yes.
Yes.
Yes. Yeah, you're right. At least in the clean room that we use, we can do it. It like this contamination protocol is very clean room specific, so it might not be the case in some other fabs. I don't know. Right. So level 1 RCA clean wafer being brought back to level 1 wet bench after lithography. So here you're not putting any metal. You just put just did lithography step. Uh, yeah, and now you're bringing it back.
Yes.
No, because then we have still put photoresist on top of it, right? So we cannot bring. The right process, if you really want to bring it back, will be to first clean it at level 2 and then bring it back to level 1. So this is the right one. So you first you bring it to level 2 at bench after lithography step. Then you can, based on the protocol of your clean room, you can do the required cleaning at level 2, then do the cleaning at level 1. So level 1 will RCA clean of new test grade samples. Is this allowed? So these are new wafer cut pieces. Can I do level 1 clean?
No.
Why?
First we have to clean it. Oh, okay.
No, new wafers we can in general bring it to level 1 RCA. But your answer is correct. We cannot do this because it is test grade. So at least in the clean room that we use, we don't put test grade samples in level 1. So because test grade are not that pure samples, right? So level
Right.
1 we want to maintain the cleanliness for the prime grade wafers.
So for
That's
the same thing, can we use prime grade?
Yeah, for the same thing we can do prime grade. If we have a new prime grade wafer, we just diced it. We should actually clean it in level 1
Okay.
because level 3 will have metal contamination and everything, right? We don't want to spoil the wafer at the start itself.
Right. Right.
Yeah. Mhm. So last problem. Well, it's a bit long problem, so I'll read it and we'll try to do it together. So this was the assignment problem, like one of the assignment problems that I had got in, like when I did the course. So it might be helpful for you guys also. So assume you have a cylindrical rod of impure silicon that you want to refine using CZ method. So in this case, we are not um, yeah, in this case, we are refining it. So we already have a ingot or cylindrical rod. We want to refine it using CZ method. The concentration of impurities is cm per centimeter cube, and the distribution coefficient is k. So they have given us how much is the impurity, what is the distribution coefficient of the impurity. Like, assume that there is just one impurity. The length of the rod is L and its area is A. So they told us the dimensions. So now we have to estimate the impurity concentration C of the silicon ingot as a function of the recrystallized length X. So I had a rod initially. I melted it into this melt. Now I am recrystallizing it using some seed. So I put some seed and then I'm recrystallizing it along that. What am I? Yeah, so I'm recrystallizing it. Yeah, so the recrystallized length that I have done till now, they are telling it is X. So what is the impurity concentration of the silicon ingot as a function of X? So we know that like when X is very small, the impurity concentration will be very low. And as we keep on increasing X, the impurity concentration will go on increasing. So we have to find this C of C, that is the impurity concentration, as a function of X. So we have to ignore all such non-equilibrium effects, or we assume that the melt temperature is constant throughout, no diffusion, nothing. So just a simple case, we have to find C of X. So so this is the general problem. We divide it into sub problems. So first we have to melt the rod, Right. So ignoring the density differences, what is the volume of the melt? Uh, so how will you find the volume of the melt?
If it is cylinder pi r square h,
Yes.
Length and area is given.
Hello? Just a minute. Written somewhere. So yeah, so the volume of the melt pi r square h is right. So but they have already given us this area, so we can just use this as a like. Huh. So V naught I can write it as A times L. So we know that the total length was L of the rod. They told us that this length is L, capital L, and this area is A, and this is the rod that we are melting, so volume will remain the same, right? So V naught is A into L. Um, what is the volume of the melt? So this is done. What is the total amount in the number of atoms of impurities in the melt? So we have to
So
find this S naught. That is the number of impurities. So what all did they give us? They have given us the concentration of impurities. That is Cm.
Cm by volume.
Cm by volume. So Cm into volume, right? So concentration is per centimeter cube. So if I just multiply it with volume, that will be the number of
Yes, yes.
impurities. No? So this is the number of impurities. Just to write it in terms of Al, I can write it as Cm Al. So next question. As you grow the crystal, what do you expect will happen to the amount of impurities in the melt? Will they increase or decrease? So this we have already
Remain
discussed. Huh?
remains same
Uh, amount of
in the
impurities
total
in the
melt.
melt. In the melt, will they remain the same? So the here we'll assume that this K is less than 1. So now what do you think?
Will be lesser, will decrease.
no, it will be more
It will
in
increase.
the
So,
melt.
I like just to recapitulate. If K is less than 1, that means impurity likes to live in the melt and the solid will be purer. If K
Yes,
is,
yes, yes.
uh,
Yes, yes, I understand.
you remembered it. Uh-huh. Yeah. So, so will it, what was the question? So as you grow the crystal, what do you expect will happen to the amount of impurities in the melt? They will increase.
If k is less than 1, if k is
Yeah.
more than 1, then it will be the other way around.
Yes, you're right. So, yeah, we are doing this entire problem assuming that k is less than 1. I forgot to mention it in the uh last slide. So, the next part. Now, what we are doing is we have the melt. We are pulling the uh, we are doing the recrystallization of the ingot. So here, what are we assuming is we assume that the area. So the area of the ingot remains the same as the area of the rod. Okay, that is an assumption that is just for simplifying the calculations that we are making. So you can think of it like we are pulling it at a rate so that the area remains the same as the original ingot. Okay, so now we are slowly drawing and drawing the recrystallized ingot from the melt. So we start from x equal to 0 position, that is the seed. After some time, you have grown a crystal of length x. So after some time, my ingot is of length, so if this is the melt, this length is x. So at this point, the total amount of impurity in the melt is S of x. So this is my melt. Um, so we had first calculated the total amount of impurities in the melt. Now, since we have removed uh, some of the solid, this S naught would have increased. So let me call that S naught as some S of x. So I'll just write it down. Total amount of impurity in the melt. So you understand why it is a function of how much solid we have crystallized, right? So x basically. So it's a function of x because the more we crystallize, the more will be the impurity in the melt. So S of x. The volume of the melt is V of x. I'll write down this also. So right at the interface between the melt and the recrystallized ingot, a small amount of rod solidifies with an impurity concentration of C of x. What is the relation between C of x, S of x and V of x? So after x has already crystallized, so now when a little bit more is getting crystallized, that concentration is C of x. So you remember initially what we wanted to calculate? Initially, the question was to estimate the impurity concentration of silicon ingot as a function of x. So, what is that? That is basically after length x, what is the concentration that is getting crystallized? So, that is this C of x. Impurity concentration at x is equal to C of x. So, um, so then what is the C of x? The C of x will depend on,
Uh,
so,
total,
huh?
sorry, S minus S of x by V of x.
What minus S of x? S
Total
naught
impurity, yes, S naught,
minus S of x.
S of x whole divided by volume, V of x.
Okay. Um, so S naught is the total impurity that was there. Minus you did so minus the impurities here. So that will give you, yes, you're right actually. But yeah, this is in fact correct. So let me leave it here as 1 for now. But what I wanted to say now was C of x will depend on your distribution coefficient K times the impurity concentration at the interface. Sorry, impurity concentration of liquid at the interface. So K was nothing but impurity in the solid times the impurity in the liquid, right? So that so then C of x I can write it as K times the impurity in the liquid. So what you said is also correct. We'll come back to it in a minute. I'm saying that we can also write C of x in this form. So then this becomes nothing but K times impurity of liquid we have from this, right? So impurity in the melt is nothing but S of x uh, but since this is impurity concentration, so this will be S of x by V of x. Does this make sense? That is K times S of x by V naught minus AX. So why did I write V naught minus AX? That V naught is the original volume minus the volume that has got crystallized. So that will give me the volume of the melt. So now let me call this 2. Now since C of x is common in both, we can equate these two. Hello? Okay, I just repeat everything. So that we are saying that total amount of impurity in melt is S of x. So uh, S of x is in the melt and volume of the melt is V of x. Okay, so then S of x by V of x will give me the impurity concentration of the liquid. Impurity by volume will give me the concentration, right? So that is the impurity concentration of the liquid. That times the distribution coefficient will give me the impurity concentration in the solid. So that is this second equation. And the first equation is basically just that, as you said, C of x is the impurity concentration at x in the solid. In solid. So that will be uh, S naught. S naught is the total impurities minus impurities in the melt. So this will give me the impurities in the solid times the volume of the solid. So V of x, uh, oh no, this part is wrong, right? V of x was the volume of the melt. We don't need volume of the melt. We need volume of the solid. So volume of the solid is nothing but um,
Ax, no?
A times x,
X.
right? But the problem now is we cannot really equate these two equations. That is because when I do this distribution coefficient thing, this is valid only at the interface. So impurity concentration at x in solid uh, is equal to the distribution coefficient times uh, the impurity in the concentration in the melt. So this concentration is varying with x, right? So this equation is actually valid only for a small increment of dx. So I think if I have an extra page, I'll write it somewhere. Sorry. Huh. So, so I have this ingot. So this length is x. Now I am increasing it by a small length dx, and this is the melt. So only for this dx, the concentration is C of x equal to k times the concentration in the melt, that is S of x by V of x. So this is valid only for this portion. So we need to write the second equation only for the dx portion. So this was uh, this was equation 2 from the previous slide. So when we write equation 1, we should write that also only for this portion. If we are writing it only for this portion, how do we write it? So what did we write here? So s naught minus s of x. So that was the uh, uh, impurities in the solid, right? So here, instead of writing the impurities in the solid as a whole, uh, what we can do is we can say that ds is the change in number of impurity atoms in the melt. Okay, just bear with me for some time. I'll just write these things down. Then ds is the change in number of impurity atoms in the melt. So when we crystallize dx portion, ds is the change in number of impurity atoms in the melt. And A times dx is the volume of this small portion. Volume of melt that crystallizes, I can write. that is A times dx. Then minus ds. What will be minus ds? So minus ds is the change in so it will be impurities that are incorporated in this small volume. So uh, so ds was the impurities in the melt. So if ds number of impurities increased in the melt, then minus ds number of impurities decreased in the solid, right? So impurities in a dx volume. I hope I make sense. So now what will be minus ds upon a times dx? So this is nothing but the impurities in the ADX volume upon the ADX. So what is this? So this is nothing but this is actually the concentration of impurities in the solid, in this much solid. So C of X is impurity concentration of solid at the interface. So do you understand what was the problem with this equation? This equation would have been true if c was not a function of x. So now since c is a function of x, we need to consider it only at the interface. Hello?
Yes, yes.
Okay then, so let's just move ahead. Uh, yeah, okay. So, so now what do we get is, so now we have, uh, so c of x is k times s of x upon v of x. So that is nothing but we can write it in terms of v naught k times s of x upon v naught minus ax, right? And c of x is also minus ds upon a times dx. So from this we get a differential equation, that is c of x is equal to minus 1 over a ds of x by dx, that is equal to, yeah, just this I'm writing, k times s of x over v naught minus ax. So this is my differential equation. Till now, is it okay? These are simple things, we are writing it in form of equations. The idea is we want to find this c of x. Now in order to find c of x, we know the relation between c of x and s of x. So c of x is concentration of impurities in the solid ingot, and S of x is in the number of impurities in the melt. So uh, in order to find C of x, what we can do is we can instead find the number of impurities in the melt, and how we can do that is by solving this differential equation that we have got by equating C of x that we got from two different equations. So, so as we crystallize it, some of the impurities get incorporated into the ingot, while the rest stay in the melt. At an arbitrary x, silicon of length dx crystallizes from the melt with ds number of impurity atoms. Can you write the relationship between dx, ds and c of x? That we already wrote. Yeah. So I had made a slide for it, I forgot about it. Yeah. So now can you write the differential equation between s of x and x and solve this differential equation using appropriate boundary conditions. So again I'll write the differential equation that we had got. So we had got ds of x by dx, and there was I think another minus 1 by 8 term here, is equal to k times s of x over v naught minus ax, a into x, sorry. So this is the equation. To solve it, we will basically just integrate it from x equal to 0 to x. X goes from 0 to x. So if x is going from 0 to x, um, s will go from s naught to s of x. Right. So if I just put s naught to s of x, ds of x, I can take this s of x down here and this dx up, integral, uh, there is a minus a 1 over, sorry, k over v naught minus ax. So Sx is nothing but the impurities in the melt for a particular recrystallization length of x. Right. So what is the integral of ds by s? That is just nothing but log. It will be log s of x, and the limits are s naught to s of x. So I'll just do the maths fast. So it will be k log v naught minus ax, a times x. It's not a function of x, it is a times x. Sorry, why do I? Okay, leave it. So and x limits are 0 to x. So then this becomes nothing but log of s of x minus log of s naught, that I can just write it as s of x by s naught, right, is equal to k log v naught minus ax by v naught. So this I can just simplify by writing k log 1 minus ax by v naught. And what is v naught? V naught is nothing but a times l. So it is ax times ax by al. A cancel. So 1 minus x by l. Right. So then finally, after doing everything, what we get is s of x is equal to s naught times 1 minus x over l whole raised to k. Basically I just moved this k up here and then like equated the logs and got this. Is it okay? Just a little bit more. Um okay, so after this, so we have already gotten an equation for s of x. Now all we need to do is find c of x. So c of x is nothing but k times s of x by v of x, and v of x is v naught minus ax. So we just substitute s of x in this. So k by v naught minus ax into s naught 1 minus x by l whole raised to k. Simplify it to get c of x is equal to k. Um, so if you remember, s naught was nothing but cm times v naught from the previous question. So v naught minus ax and again 1 minus x by l whole raised to k. So now we have gotten c of x as a function of cm. So cm is the original concentration of impurities, and then all the other parameters are the parameters that we know. Again, this v naught upon this also we can simplify. This v naught cancels 1 and this will become x power l, just like the previous case. Like the maths you can do on your own. I just write the final answer here. So this will be cm k 1 minus x over L, and there will be a k minus 1 term coming from this portion. Yeah, that's it. So now we have Cx. Uh, so we have found Cx. So that is what we were trying to find, right? The concentration of impurities in the ingot as a function of x. X is the recrystallization length. And if I just plot this Cx over Cm, so here it is Cx. If I just take this Cm down and plot it like Cx or C of x upon Cm, uh, so that is my y as a function of x over L. So this x-axis is nothing but, so the recrystallization length upon total length. So 1 means entire ingot is recrystallized, 0 means nothing is recrystallized. So we are just starting at the seed. And if I plot this for different values of k, so k is the distribution coefficient. Now all these three examples, k is less than 1. So so naturally, for a very long length, we find that Cx is actually, so the concentration of impurities, so impurity concentration is lesser than what we started with. Uh, so what I mean to say is, so if you look at the k equal to zero point 0.4 curve, so this is the blue line. So at 0.8, so when 80% of the ingot is recrystallized, that is when the concentration of impurities starts to become equal to the original impurity concentration. So for the first 80% of the ingot, it is purer than the original cylinder, and after that it becomes uh, after that it becomes less pure than the ingot. So this point is reached at 80% in the case of k equal to zero point 0.4, the distribution coefficient of 0.4. But as we go on reducing the distribution coefficient, we see that longer and longer lengths of the ingot will be purer. So now you can get an idea about how the distribution coefficient helps us in achieving like more amount of pure silicon. So the lower the K value, the better it is for the zone refining method. Choklovsky. Okay, so was that clear? So that was the whole point of doing this entire exercise. We found out how to find out C of x as a function of x, and we saw like the effect of K on the impurity concentration. Hello?
Yes.
Yes, so that's it for today. Um, do you have any questions?
Can we get this PPT?
Sure, sure. I'll share a drive folder link. I think you will get it on the NPTEL site itself. They will post it. Or I can do something. I'll share with you now. I just made a drive.
Thank you.
Yeah, I'll put it in the chat.
Also, will recording be available for the sessions?
Yeah, I'll put the recordings in this folder actually. The PPT also,
Okay.
I'll make a subfolder inside and put it there then.
Okay, okay, thank you.
Yeah, no problem. So yeah, I have put the drive link. You can copy it. So there are a lot of comments actually. I'm seeing them just now. Uh, so anyone wants to ask? Is Abhishek there? I'm sorry, Abhishek. I was not reading the comments. So what were you saying about the CZFZ? Um, Okay, I think I might have answered this already. About WhatsApp group, yeah, we can have a WhatsApp group. Uh, just that I don't know how to share the link with everyone. Let's see, like by the next class, if the NPTEL people are fine with it, we'll make a WhatsApp group.
Okay, thank you.
The folder is not opening, is it? I'll make it open access. Sorry, like I just made it, so I don't know the access options. Okay, so let's meet next week.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.